Imagine a world without screens. A world in which you get your information from paper, like the vast majority of human history. Screens surround us in our lives, perhaps even sometimes too much. They are on your TVs, phones, tablets, laptops, drones, in hospitals, in advertising, in factories, everywhere. Many of these screens rely on basic LED technology. Light-emitting diodes are the result of applying semiconductor physics to make colored light. Diodes have an enormous amount of applications in electronics, and we will use our understanding of semiconductors to delve into these today. So keep your eyes on the screen as we unpack this. This is Think 4. When we create doped semiconductors, we add or remove additional electrons which lurk just outside their conduction and valence band in order to make the flow of electrons easier. To make semiconductors really useful, we need to combine these N-type and P-type semiconductors. If we sandwich them together, we create a P-N junction. This is the foundation of all modern electronics, because this creates a diode. When we make a P-N junction, the additional electrons from the N-type semiconductor fill the holes in the P-type. This makes the P-type slightly negatively charged and the N-type slightly positive. In this area, there are no more free electrons or holes, and we call it the depletion zone. This creates a small potential difference or voltage across the junction. This is typically about 0.7 volts, and we call this the barrier potential. Now, if we take this P-N junction and connect it to a battery, two things can happen. One, the N-type is closest to the negative terminal of the cell, and the P-type is closest to the positive terminal. In this instance, the electrons flow out of the negative terminal towards the N-type. Any holes in the N-type are filled by electrons from the cell, and a current flows. If we orientate the junction this way, it is called forward bias. 2. The junction is orientated the other way around, with the P-type closest to the negative terminal. This time, the holes in the P-type are filled by electrons from the cell and no movement across the junction occurs. There is no current flowing. This is called reverse bias. This P-N junction, therefore, allows current to flow in only one direction around a circuit, depending on its orientation. This is a diode. The last thing you need to consider is the case of a special diode, an LED. In LEDs, when the electrons and holes move across the junction, sometimes they combine and this releases energy in the form of a photon. The energy of the photon depends on how big the band gap is for that material. A big band gap releases a high energy photon, so blue or violet, whereas a small band gap produces lower energy photons like red. It is worth remembering that the band gap determines the color of the light emitted, and one semiconductor can only release one color of light. Without the technological input from LEDs, our world would feel very different. By manipulating the physics of semiconductors, we make light, and in doing so, we make windows of communication. That said, screens are not everything, and despite the exciting physics, I would strongly encourage you to relax without one for a while. Pick up a book or go for a walk, and just occasionally, leave your phone behind. This was Think 4. Thanks for watching.